Okay, so this is the case study data science sort of thing to look at the end of chapter 4. So what we're going to do today is we're going to look at a thing called linear discriminant analysis, and we're going to use it to predict genre in music. So what we're going to do is we're going to get some data from Spotify. Now, if you're interested in doing this yourself, you need the Spotify package. At the moment, you have to get that from GitHub. It is on CRAN, but it doesn't seem to be available for the latest version of R. So if you're using the latest version on, you have to use the GitHub until that's updated. You're also going to have to set yourself up a Spotify access token. There's instructions in the package on how to do that, and that gives you permission to go and ask Spotify for data. So what we're going to do is we're going to look at 3 genres. We're going to look at punk, grime, and disco. And I've written 2 functions to do this. This function, if I give it a artist ID, it will go to Spotify and it will get every song they've ever done, drag it down, and it will grab information about that song of when it was produced, how loud it is, what key it's in, everything. The other thing I'm going to do is I've written another function here that I give it a genre and it will just go and grab 20 artists in that genre. So these 20 artists have been classified as that genre. It will grab them, and then once it's grabbed their IDs, it uses the previous function to go and get every single song. So what I've done here is this goes and grabs basically 20 punk artists, gets all their songs. We get 20 grime artists and all their songs, and 20 disco artists and their songs. Now, this takes time to do, each of these to run, so I've done it all before, and we can now run this. This has now been saved, and it downloads it. And you can see the ones I've got artist name, the year it was released, the album release, danceability, loudness, duration, genre. Just going to do a little bit of cleaning here. First of all, when I played around with this before, I found that the best predictor genre were year and danceability. And I've kept the genre, so I've got rid of the artist name, I've recleaned the year. So now it's just called year as opposed to album, and we've got danceability. So the things we're going to do is we're going to do a little bit of EDA, or exploratory data analysis. So first thing I wanted to look at is, when I run this, how do our genres look over time? So what we've got what we call a kernel density smooth, but basically these are sort of smooth histograms or densities of the years on the axis and how much. So you can see the songs they've chosen for disco, a lot of basically a peak, sort of 70s, 80s. You'll notice the colour I've used, nice hot pink for disco there. And then we've got another peak around the late 2000, before 2010, so 2007, 2008. Punk, it's gone for next gen sort of punk. So it's not gone for your classic punk, which would be in the 70s. The ones it's grabbed here, I've gone for a nice fire brick angry red for punk. Got a couple of peaks here all about. So it's a sort of modern punk. And then grime has really only been in the recent years, but here we've got a peak around about 2010 and another peak about 2017. What about danceability? Well, with this one, you find that the main differentiation is that punk is a lot less danceable. Both grime and disco, obviously a lot of danceability. How they measure danceability, go to Spotify, have a look, they'll explain it. The other thing I've done here is I've do a bivariate plot where I'm going to look at these 2 things together. And I put a G on smooth. It's a bit busy this, but you can see generally, if you're looking at earlier time, it's mainly disco. As we get later, we start to see both grime and punk appear. And the way this is separated is grime is a lot more danceable than compared with punk. As I said, this is late punk. Early punk, you're really looking late 60s, early 70s for this first gen. Then it hit the UK about 1976. But the artists he's chosen are more late punk. So we're going to do a linear discriminant analysis. So let's go and actually have a look at this. Let's set up our model. So what we're going to do is we're going to consider the ith song. And we have 2 predictors we're interested in. The first one is the year of that song and the danceability. And for each song, we have the class it's in, which is our response variable, or yi. And obviously in this case, it has 3 possible levels: disco, grime, and punk. So this is a classic classification problem. We've got two predictors. We want to use those two predictors to predict what genre a song is. So let's think about this using our Bayes. We want to calculate the probability that our random variable y equals k given our x equals x, where x here is going to be your year and your danceability. Well, using our Bayes, we can rewrite this as the probability x equals x given y equals k, probability y equals k, and then we've got to divide by our sum over all possible classes. So this just gives our overall probability that x equals x by taking into account condition on each class. Change of notation here, I'm going to rewrite the probability that y equals k as just pi k. So we need to assume a distribution. We want to say, how does year and danceability, how is it distributed for each class? And we're going to look at the stuff we've used in this chapter. We're going to look at the bivariate normal. So we're going to say the probability that x equals x given y equals k. So given that we're in the kth class, we're going to assume that the x, the year and the danceability have a bivariate normal distribution. They have the same variance covariance for every class, but they have a different mean for each class. So this is our bivariate. And if you think about it, when it comes to this, we just want to work out this probability. But what you could do is you could just work out the top bit for each class and then assign the class for that individual prediction on the highest value. Because that would be the one in this that would give you the largest probability. So that's what we're doing. We're going to make what we call a discriminant function. We're going to calculate this top bit here. Well, because we only care about finding the largest one of the ways we can make it easier is we can take logs. And so if we take this term and we take logs and you take your distribution and you rearrange it, I'm not going to do it in this. If you're really interested in that, we'll be looking at in data science in third year. What you end up is this discriminant function. What this function does is you can take a value of your predictors, you can shove it in this function and it will give you a value for each class. And then you're going to assign the class that has the largest value of this. But if you look at this function, right, we're going to put in our predictors, but we need sigma, we need mu, and we need pi. So how are we going to get that? Well, we're going to use our training data. We're going to use the labeled sets that we have. So how can we do that? Well, first of all, what you can do to get your mean vector. So this is going to be a vector, a column vector with two entries, which is for each class, it's going to give you the mean year and the mean danceability. We're just going to add up all the values and divide by how many. So this is just a vector sample mean. Here is our variance covariance. We're going to do it by looking at the sum of the squares. This is in vector notation, but basically taking each observation, taking off its mean, squaring it, adding them all up and dividing by your degrees of freedom. And pi, we're just going to take the number of observations that are of each individual class and divide by the total number of observations. Okay? So you can see this is just a nice use of the bivariate normal that we saw in this chapter. Let's go and actually look at how we do that. So now, well, we could do that by hand. I'm not going to do it. I'm going to use the LDA, which is the linear discriminant analysis function. Our genre is what we're trying to predict, and we've got two predictors, year and danceability, and our data's here. So we run this, and we get our output. You can see that it has your pi's here, it has your means. The sigma's not as obvious to get out, but how well is this? Well, what I'm going to do is I'm going to use this model to predict for each value that we have in the data. I'm going to now say, well, how does our prediction compare with the facts? So what have we got here? So of all the songs that are disco, it's correctly classified about 3,500 as disco, although it has taken 600 of these songs and said they're grime and 1,000 and said they're punk. So anything that's on the diagonal here is correctly classified. The ones that are off are incorrectly classified. So it's not too bad. What we can do as well is we're going to have a visualization of how good this is. So what I'm doing now is I'm predicting over a whole grid of values. And what we've got now is we've got our year on the x-axis. We've got our danceability. And basically, if you look at these areas, anything that's in this pink area here, it will automatically classify as disco. So this is, as you can see, it's early and more danceable. Over here, we've got the area, the region that would be classified as grime. So this is obviously more danceable because it's up and towards the right, so it's later. And then we've got our punk. What I've done now is I've overlaid that with the actual dots with their real values. So you can see we've got a lot of pink dots lying in the pink region. We've got quite a few blue dots lying in the blue region and quite a few red. But you can see here that, it's not quite getting it right. And one of the problems is with linear discriminant analysis, when it creates these regions, they are separated by a line, hence linear. As you can see, it's not quite right. This is a bit more. And one of the problems is we assume the variability is the same for each class, but you can see that disco is a lot more variable than, say, grime, which is a lot less variable than, punk. How could we improve it? Well, we could say, well, let's get rid of that assumption that the sigma is the same for every class and have a separate sigma for each class. And that gives us what we call QDA. So if I run that, now we add our predictions for QDA and we have a look. Well, if you compare, it's looking a little bit better. We're getting more along the diagonal. But what's interesting is we'll look at the same plot now. Take a bit of time. And now what we get, instead of straight lines separating them, we get curved ones. And that's what QDA stands for. It's quadratic discriminant analysis. You end up by not assuming the same variance covariance for each group. You get these curved lines. And now you can see this is starting to come down this blue region to try and grab these grime. So you are LDA, a very nice, simple, very fast actually classification method, and one that uses the bivariate normal that we saw in this chapter. Okay, see you next time.